Good afternoon, everyone. Neurosurgical navigation devices are used in almost every operation. However, 85% of the cases, they fail the surgeons. Why? They are static and cannot adapt to the brain deformation during the operation. It's really like using a Google map. It's really like using a paper map to go in a city with constantly changing traffic. A state-of-art neurosurgical navigation system comprises of surgical planning, where the surgeon can use to plan the surgery and the trajectory to the tumor before the operation, camera sensors, and the surgical navigation. But the brain is an ultra-soft tissue. During the operation, the brain will deform. This means that the location of the tumor will shift. As a solution, the surgeons are either forced to rely on their expertise to find the tumor and extract it, or to bring intraoperative imaging to the operation room, rescan the brain, and update the system. They can use ultrasound scanners or MRI, and in some cases, CT scan, which leads to longer operation, higher cost, larger incision for the patient, longer recovery time for the patients, and finally, in case of CT scan, extra radiation dose. At EVA, we want to change all of that. Our vision of a surgical navigation system is to simplify it again, go back to the sensors, planning, and the surgical component. Thanks to our advanced system, we can track the deformation of the brain and the tumor in real time, which enhance the patient outcome. How do we know all of this? We worked with neurosurgeons in Luxembourg, in France, in Germany, in Jordan from day one to tailor our system to their need. And we can see that they supported us with endorsement letter showing the necessity of EVA's solution and complaints about the current technological gap. We also signed pre-collaboration agreement with them. In this collaboration agreement, we agreed that we will conduct our clinical trials with them in return of changing to a contract when we get the CE marking and the FDA marking and start our sales. At EVA, thanks to our advanced technology, we can track the location of the tumor and the brain during the operation. This means real-time adaptability, radiation-free precision, enhance the surgical precision, and there is no interruption for the workflow of the neurosurgeons, which is very, very important for them because they really don't like to stop the surgery, go to the MRI, rescan, and come back. It wastes time, and it costs a lot of money. And finally, this means shorter surgery time, cost, and lower risk for the patients. Recently, we finished the first component. This is the pre-operative component. In this component, we can predict and anticipate the location of the tumor in the brain before the surgery during the planning process. This prediction depends on the tumor characteristics, and it depends on the cranotomy planning that the surgeon decides. This means it's a patient-specific scenario. This feature is unmatched by any of our competitors in the market, and we filed a patent recently. The serviceable addressable market by 2030 for neurosurgical navigation system will reach 3 billion plus, with a total addressable market of 18 billion. And we think that EVA, with its technology, we are positioned perfectly to gain a good share of this market. We are a team of co-founders. We are expert in biomechanics, me and Stefan, in computer vision and tracking, Morris, and in marketing and strategy, Natalie. And we have enough expertise to bring EVA to the market. Our business model relies on 3 pillars: system sales, where we sell our system, and to sustain a constant profit and revenue stream for the company, we have surgeon training program and maintenance contract of our system. We anticipate that we would need 5 million euro over 5 years. This money will go to R&D, clinical trial, regulatory process, and QMS. Thank you very much.
Hi, thank you so much for the presentation. It's really interesting. You talk about tumor. What about also, I don't know, other application like resective surgery for epilepsy, laser, intraparenchymal thermal therapy, and so on?
So the current gap in the system, in the technology right now, and the neurosurgeons, they complain about a lot is the tumor. So, and that's why we want to tackle this problem first. When this problem is tackled, we could expand to other part of the human being body. For example, we can go to the spine, we can go to aneurysm, and some other parts.
I had a hard time following. What's the core technology? Is it based on medical imaging? Is there algorithms that? So what is being tracked here? I just didn't follow that.
The neurosurgical navigation system, you have two components. You have the preoperative planning part, and you have the intraoperative one. In the planning one, the current state of art is to bring the MRI scans, because you need to do the surgery, so you already have them available. You insert them to the system, and the system will do a three-dimensional rendering of the brain and the tumor, and then the surgeon will decide on the trajectory. What we did is the following. So we already did all of this, like normal traditional way, and then we added 2 points. The first one, the surgeon can tell the system what kind of tumor is there, because what we are solving physical equations. We treat the brain as living tissue. And the characteristic of this tumor can really influence the deformation. The second part is we give the surgeon the ability to adjust the brain virtually and the skull, exactly how he wants the skull to be in the operation room, and draw the cranotomy. And according to this cranotomy drawing, the tumor characteristics, and other parameters, we can predict the deformation during the planning process, meaning that the surgeon can see how the brain will deform even before going to the surgery. And for example, he can even change the scenario, change the cranotomy, the size of the cranotomy, the position of the cranotomy to see, you can play around with the system to see how the deformation, how the tumor location will change. And then we go to the operation room. We have sets of sensors. Those sensors will be used to enhance the precision of our system. And currently, we are talking about an error of 0.8 millimeter in our planning.
Thank you.
Thank you for the pitch. I understood your product MVP as the surgical process improvement enterprise model. So I want to ensure that you are targeting the right decision maker. Would it be the surgeon who wants to adopt this technology, or would it be the hospital administrator?
It depends. When I say I'm talking to the surgeons, for example, we saw that there's Professor Frank Hertel. He's the head of neurosurgery department in Central Hospitalier de Luxembourg, which is the biggest in Luxembourg and the surrounding region between Germany, France, and Belgium. Of course, when I talk to him, we are talking to him because we want to see the problem and try to find a solution. But at the same time, we also talk to the director of the hospital. So when we sign the pre-collaboration agreement or we agree on anything like that, we talk to the directors of the hospitals. Also, for example, in Luxembourg, we are working closely with the Ministry of Health, and we are working closely with the Ministry of Economy. And there is a body in Luxembourg called Lux Innovation. It's for startups. And there is a health cluster there that we also work closely with them to tailor all of this to the need of the country and the hospital. And after we manage this, we can expand. For example, if we have the collaboration with Toulouse Hospital, with the neurosurgery department there, we talk to the director, and from there we will take it further to talk to the ministry itself. So it really depends country to country, because some countries the hospital can really acquire, like in Luxembourg, but if you go to Germany, you need to talk to insurance companies.